Welcome to our Quantum Deep Dive. Today we're plunging into a really fascinating intersection where reinforcement learning meets quantum computing. We're digging into an essay by Jürgo Schneppat titled Hybrid Classical Quantum Reinforcement Learning, Zukunftsfähige AI. Think of it as a shortcut to understanding how combining these fields might just shape the future of AI.
Yeah, it's really about looking at the, incredibly successful world of classical reinforcement learning and asking, can quantum mechanics give it a kind of supercharge? We'll explore what Schneppat says about that and what it could mean, whether you're just curious or, need to get up to speed fast.
Okay, let's set the stage a bit. First off, reinforcement learning, RL. The essay defines it pretty clearly. It's that machine learning tech where an agent learns by basically interacting with an environment.
Right. Trying to get the most rewards, avoid penalties, trial and error, but guided by a goal. Schneppat mentions examples like robotics, finance, autonomous driving, game theory.
Right, like DeepMind's AlphaGo beating the World Go champion. That used deep neural networks and Q-learning, a classic RL technique.
Exactly. So it's powerful stuff.
Especially for problems where you don't have a rule book, you just have to kind of figure things out as you go.
Precisely. The agent learns the best strategy, the policy, often using math models like the Markov decision process, states, actions, transitions, rewards. And the learning often involves optimizing value functions or Q functions using things like the Bellman equation.
Okay, so it's powerful, but here's where it gets interesting. Classical RL, despite all its wins, it has some pretty big limitations, doesn't it?
Yeah.
Schneppat points out a few key ones.
Yeah, absolutely. The first one is the sheer computational effort. RL can need immense resources, especially in complex situations. An agent might have to run through thousands, millions of episodes to learn anything useful. It's often just inefficient for many real-world tasks. Takes too much time, too much memory.
The famous curse of dimensionality. That essay brings that up explicitly.
That's a huge bottleneck. When you have environments with just vast numbers of possible states or actions the agent can take, the computation needed just explodes. It grows exponentially. That Bellman equation, QR plus GOSA, well, it becomes computationally impossible for really large problems.
And then there's that tricky balance, right? Exploration versus exploitation. The agent needs to try new things, but also stick with what works.
Exactly. Finding that balance efficiently can really slow down the training process. It's a fundamental challenge.
And one more thing, classical agents trained in one place often struggle if the environment changes, right? Transferring knowledge is hard.
That's right. They can be quite brittle. Adapting to dynamic conditions isn't their strong suit.
Okay, so those are some serious roadblocks for classical RL. How does quantum computing even, enter the picture here?
Well, quantum computing operates on totally different principles. It's not just faster classical computing. It's about leveraging quantum mechanics, things like superposition, entanglement, quantum parallelism. These allow quantum computers to process information in fundamentally new ways, potentially exploring many possibilities at the same time.
Right. Superposition means a qubit can be a 0 and a 1 simultaneously in some sense.
Exactly. Like Solaro wrangle plus the 0-1 wrangle. For RL, imagine using that to evaluate multiple states or actions all at once. That could dramatically speed up calculations.
And entanglement, that spooky connection between qubits.
Yeah, that non-local link. It could potentially allow for more efficient ways to store and process complex relationships or correlations within the RL agent's knowledge, maybe improving pattern recognition.
Schneppat mentions some specific quantum algorithms too, like Grover's for search and Shor's for factoring, kind of as context.
Yeah.
But he really highlights the quantum approximate optimization algorithm, QAOA.
Yeah, QAOA is seen as particularly promising because it's designed specifically for optimization problems. The math, like that Hamiltonian H equals to C plus HHM, looks complicated, but the core idea is using quantum evolution to find good, approximate solutions to hard optimization problems.
Yeah.
And RL is full of optimization problems, like finding the best policy.
So this deep dive is specifically about hybrid classical quantum RL, which means we're not talking about replacing classical RL entirely.
Exactly. It's about combining them. The hybrid approach aims to use quantum's potential strengths, the speed-ups, the optimization capabilities to specifically tackle those bottlenecks in classical RL we just talked about. Things like the computational complexity, the curse of dimensionality. It's about augmenting classical methods, not replacing them wholesale. At least not yet.
So what do these hybrid systems actually look like? How do you mix the two?
Well, the essay outlines a few ideas. One way is quantum-enhanced classical RL. Here, your main RL agent is classical, but it offloads specific, really hard parts of its job to a quantum processor.
Like what sort of parts?
Maybe a particularly complex optimization step using QAOA, or perhaps using quantum effects to speed up the exploration phase, or using variational quantum circuits, VQCs, to help approximate functions.
So the quantum computer acts like a specialized coprocessor for the really tough bits.
Kind of, yeah. Another approach is more integrated, hybrid quantum RL agents. Here, quantum components play a more direct role, maybe using things like quantum Boltzmann machines for representing policies or value functions.
And the essay also mentioned using quantum simulations for RL.
Right. You could potentially use a quantum computer to simulate very complex environments that are hard for classical computers to model accurately, and then train your RL agent within that quantum simulation. Or maybe develop better transfer learning models. The key idea is using quantum subroutines like quantum-assisted sampling, maybe leveraging Grovers for finding relevant states faster, or quantum policy gradient methods to accelerate specific parts of the classical RL loop.
Okay, let's talk payoffs. If this hybrid approach pans out, what are the really big potential advantages?
Schneepat highlights several exciting possibilities. First, those potential exponential speed advantages. That quantum parallelism we mentioned. It could mean processing many states or trajectories simultaneously. Instead of classical search taking, say, ON time, a quantum approach using amplitude amplification like Grover's algorithm might achieve ON in certain cases.
That's a significant leap, not just a small improvement.
It could be. Second, improved optimization. Quantum algorithms like VQC or maybe QAOA could potentially navigate complex optimization landscapes more effectively than classical methods. They might be better at finding the global optimum, avoiding getting stuck in those suboptimal local minima that plague classical optimization. This could lead to better policies or value function approximations.
And going back to that curse of dimensionality, the complexity issue.
Quantum approaches might help there too. Entanglement could potentially provide a more compact way to represent complex correlations between many state variables, and superposition allows for parallel evaluation strategies. This combination could make learning much more efficient, especially for those huge problems in robotics, finance, logistics, where the number of possibilities is just astronomical.
That all sounds incredibly promising. But I sense a big but coming. What are the major hurdles? The essay must detail the challenges.
Oh, absolutely. And Schneepat is very clear about these. There are significant technical challenges. The number one issue right now is the hardware limitations of current quantum computers. We're living in the NISQ era, noisy intermediate scale quantum.
NISQ. That means not enough qubits, lots of errors. Qubits don't stay quantum for long.
Pretty much sums it up. Current systems have, maybe dozens, perhaps low hundreds of qubits. They have short coherence times, meaning the delicate quantum states decay very quickly. And the quantum gates, the operations, they have low accuracy. They're error-prone. They just aren't reliably scalable yet for the kind of complex, long computations RL often needs.
So dealing with noise and the need for error correction is a massive problem.
It's critical. Quantum computations are incredibly sensitive to noise from the environment. Reliable, large-scale quantum computing will require quantum error correction, QEC. But QEC itself is extremely demanding. It needs many physical qubits just to encode one protected logical qubit. We're not there yet with NISQ devices. They are inherently noisy, which is why hybrid approaches that try to work around the noise are so important right now.
Okay, hardware is a big one. What about the theoretical and algorithmic side? Are the quantum algorithms ready for RL?
That's another major challenge area. There's still a limited availability of quantum algorithms that are specifically tailored for RL tasks. Many existing quantum algorithms are for more general optimization or simulation tasks. Adapting them effectively for things like policy iteration or value function updates in RL is an active area of research.
And does the theory actually guarantee a quantum advantage for RL?
That's a key point Schneepat makes. There's largely a lack of formal proofs for quantum advantage in RL. We have theoretical reasons to believe quantum could help, and some promising algorithmic ideas, but we don't yet have rigorous mathematical proof that quantum approaches will offer, say, an exponential speedup for all or even most relevant RL problems, or clear definitions of the conditions under which a quantum agent is definitively better. A lot is based on heuristics and promising early results, not proven guarantees across the board.
And just stitching the two systems together, the classical computer running a main loop and the quantum processor doing its part, that must be complex.
Absolutely. The integration itself is a significant hurdle. How do you efficiently transfer data between the classical CPU and the quantum QPU? How do you synchronize the different parts of the computation? These are complex, algorithmic, and frankly, engineering problems that need solving for hybrid models to work smoothly.
Okay, so massive challenges. But despite that, the essay mentions some early research, some actual experiments. What are people finding in these initial studies?
Yeah, the research is still young, but there are some interesting, albeit preliminary, results. Schneppat cites work like Chen et al. From 2022, who use variational quantum circuits, VQC, for policy optimization. They ran simulations and even some small experiments on actual IBM Q hardware for a simple grid world problem. And they found that their hybrid VQC-based models seem to converge maybe 30-40% faster than the classical counterparts.
Faster convergence is definitely a good sign, even if it's on a simple problem.
It is. And another study you mentioned, Jerby et al. From 2021, looked at quantum-enhanced exploration. The idea was using quantum principles like superposition to evaluate multiple possible action sequences simultaneously. Their simulation suggested this could potentially reduce the number of episodes, the amount of interaction with the environment needed for the agent to learn effectively.
And QAOA comes up again here, too.
Yes, using QAOA to optimize value functions or policies is another active area. Early experiments suggest that QAOA-based hybrid models might, in some cases, reach a stable optimum quicker, perhaps finding better approximations using those Hamiltonian functions.
So pulling that together, these early comparisons show some potential speed up, maybe better optimization on small scales, but the hardware is still the big limiting factor.
That's really the key takeaway from the experimental work discussed in the essay, yes. The theoretical potential is compelling, and these initial experiments on NISQ devices show some promise in controlled, limited settings. But scaling this up to tackle complex, real-world RL problems, that's where the current hardware constraints really bite.
Thinking ahead then, if and when the hardware improves, where might we actually use this hybrid RL? What are the potential killer apps?
Schneppat lays out several possibilities where the complexity seems well suited. Robotics is a big one. Imagine faster learning for autonomous control, complex manipulation, or motion planning in cluttered environments. Finance is another, potentially analyzing incredibly complex market interactions, optimizing trading strategies, or managing risk more effectively.
Makes sense. What else?
Logistics think optimizing vast supply chains, vehicle routing, or traffic management systems, especially those that need to adapt quickly to changing conditions. And also areas like quantum chemistry and material research. Here, RL could be used to guide the search for new molecules or materials with desired properties, potentially leveraging quantum simulation capabilities too.
So looking out towards that future, what really needs to happen for hybrid RL to go from, promising papers to actual practical tools?
Hardware, hardware, hardware is the mantra. The essay is clear on this. We need significant leaps in quantum hardware development. That means increasing the number of high-quality qubits, maybe getting towards the 1,000-plus range and beyond, drastically improving coherence times so quantum states last much longer, developing effective, scalable error correction to reach fault tolerance, and also the continued growth and accessibility of quantum cloud platforms, like those from IBM Quantum, Google Quantum AI, and others, so researchers can actually experiment.
And the ultimate goal is achieving that quantum advantage, but specifically for RL tasks.
Yes, that's the potential inflection point, where we can demonstrably show that for certain important RL problems, a quantum or hybrid quantum approach performs significantly better faster, or finds better solutions, or handles more complexity than any classical computer ever could, whether that's through speeding up policy optimization, radically improving exploration efficiency, or perhaps modeling complex probability distributions more naturally using things like quantum Boltzmann machines.
But as you said, proving that advantage rigorously for RL is still very much an open research question.
It absolutely is. We don't have those formal proofs of exponential speed up across the board for RL yet. And the true scalability on large, fault-tolerant hardware just hasn't been tested because that hardware doesn't exist yet.
So what are the really big burning questions for researchers moving forward in this space? What keeps them up at night?
Schneppat's essay lists quite a few. A big one is, Which specific RL problems are actually best suited for quantum acceleration? It probably won't be everything. How do we develop better mathematical models and tools for applying quantum mechanics to RL? Can we formally prove quantum advantage for specific RL tasks and define the conditions? What are the most effective hybrid architectures? How do we best combine classical and quantum algorithms and handle that data flow? How can we develop better error mitigation techniques specifically for quantum RL even before full fault tolerance? And then practically, which real-world applications are likely to see the first benefits? And what role will cloud quantum computing play in making this accessible? Lots to figure out.
But if, and it's a big if, these challenges are overcome, what could the long-term impact on AI and machine learning look like?
Potentially profound, really. Schneppat suggests it could revolutionize optimization within RL, maybe enabling solutions to problems currently considered intractable. It could lead to entirely new hybrid AI architectures that seamlessly blend classical and quantum processing in ways we haven't fully designed yet. This could significantly advance autonomous systems, think self-driving cars, sophisticated robots, and ultimately it might even lead to entirely new learning paradigms that go beyond the current classical approaches we rely on.
Okay, so to wrap things up, hybrid classical quantum reinforcement learning is clearly a field buzzing with potential. It's trying to merge the proven learning strategies of classical RL with the, well, frankly, weird and powerful capabilities of quantum mechanics.
Yeah, the aim is to unlock faster, more efficient, maybe even fundamentally smarter AI. As Yargo Schneppat's essay makes clear, there are huge hardware and theoretical hurdles still ahead, significant challenges. But the early research is promising. It suggests a future where this hybrid approach could let us tackle incredibly complex problems that are just beyond the reach of today's classical computers.
It's definitely a frontier of AI research, and Schneppat's essay gives a fantastic snapshot of where things stand and where they might be headed.
Yeah, the question it really leaves you mulling over is, how fundamentally will quantum mechanics change the way our machines learn and solve problems in the coming decades? It's a big one.
A very big one indeed. Thank you for joining us for this deep dive.
Goodbye for now.